Thanks for inviting me to FU and for the group meeting talk. I should apologize to everyone who were looking forward to Nathan's talk. So let's get this. Today I'm gonna talk about this project, quantum dynamic programming, that I've done with Marek, Ryuji, and Nelly. Nelly is also there, I think. Okay. Yeah. So before I start the talk, for the later discussion, I'll briefly introduce myself. I'm a PhD student at NTU Singapore, working with Nelly, and we have this like bustling wildlife on our campus. So if you visit us, just check out the animals.
But these are not your colleagues, right?
Yeah, and my PhD is about exploring the power of auxiliary systems in quantum information processing tasks. So I've been working on using auxiliary systems catalytically in the resource theoretic approaches, and also using auxiliary systems as the instruction for quantum circuits, which is the topic of today's talk. And for example, I'm discussing with Julian and Nathan on doing this on optical settings, and I'm also interested in this circuit complexity business that I believe your group is also doing. So yeah, please approach me for discussion. I need them. And yeah, so our reviewer told us that we lacked the punchline in our manuscript. This is the punchline. So basically, we can solve certain problems with exponentially shallower depths, but at the cost of exponentially larger widths compared to the conventional approach without this dynamic programming. So I first will introduce what kind of problems we can solve, and we call them quantum recursions. And recently we put a paper on arXiv on quantum imaginary time evolution that can be formed as a quantum recursion. So we will introduce quantum recursion with that algorithm, and then we will show how to do this exponentially shallow depths and exponentially larger widths using quantum dynamic programming. And we will argue why that can be nice in the context of distributed quantum computing and some hybrid strategies. So here hybrid is not like classical quantum hybrid, but hybrid of conventional approach and our approach. And we will show you some other examples. Okay, so this is like a separate project on quantum imaginary time evolution that I've done with Marek, Bihong, Yudai, Doi, and Nelly. Sadly, you cannot see the meme very clearly, but this is a very nice meme made by Zoe. So basically, the paper is about compiling quantum circuits that implement the imaginary time evolution without any need of variational optimization or blocking codings, etc. So yeah, we are threatening approximate ground state preparation schemes. So yeah, basically imaginary time evolution is this unitary evolution of the state, continuous evolution by this parameter beta. And psi of beta should be proportional to exponential of minus beta h applied to psi of 0. And because this is not a unitary operator, we should normalize the state with this vector. And if you just like differentiate this whole thing with beta, you get this differentiation where the state is evolved by this generator minus h plus average of h. So this is psi beta h, psi beta. And if you write your state in as a superposition of energy eigenstates, you can observe that as a result of this evolution, the coefficients of your energy eigenvectors will get suppressed by this negative vector when the eigenvalue of that energy is higher than the average energy. So this will suppress the higher energy eigenvectors, sorry. And as we are doing that, the average energy will also go down, right? So eventually, at the end, the ground state will be prepared, and this will be exponentially fast to the beta. Okay. So this differential equation can also be written in an equivalent form, which is this, where the psi beta is just the density matrix for the pure state psi. And as you can see, this is a nonlinear Schrodinger equation because you have the psi dependency here. And that means this flow unitary operator should be state dependent at each time, which is extremely difficult to actually implement in this like digital quantum computers. So we need several tricks to make it implementable first. The first trick we employ is the discretization of this continuous flow. So rather than evolving the state with exactly the state at the time, we kind of discretize it with a small time step. And then you can approximate this flow by this stepwise iteration. So psi of k will evolve by this operator, which is unitary. That depends on psi k and h. So this part is fixed for the duration of S, right? We discretized it, but this commutator exponential is still a bit far from direct implementation. So we need to approximate it by the technique we call group commutator approximation. This is just true. And if you are applying this to the state psi, this last term can just be global phase. And that finally, we can define this dB-kite recursion, where the state at each step is evolved by Hamiltonian evolution, the reflection around this state omega k, and another Hamiltonian evolution. Okay. We still have this nonlinearity of the evolution because our unitary operation depends on the state omega k. And that is precisely what we call quantum recursion. It is the recursive evolution of the state where each recursion step, each unitary recursion step depends on that state itself.
And sorry, can I ask a question? And that the recursion is necessarily the case because dependent nonlinear behavior.
Yes, you cannot just evolve it with the fixed operator. So Hamiltonian evolution, we just assume that it is given or this. But the problem lies on this nonlinear part or the quantum recursion part. And we cannot just directly compile this exponential of I square root of S omega k because we don't know what omega k is unless we classically simulate everything or unless we do the tomography of this state omega k. So we need a different way of doing this. And there comes this nice observation where if your recursion is defined in this way, omega k plus 1 is just like unitary that depends on omega k applied to omega k, then exponential of I omega k plus 1 can actually some product of operators that only depend on omega k, not omega k plus 1. So we can replace all the evolution by omega k plus 1 by the evolutions by omega k. We call this property like covariance. And so choosing this u of omega k as our original recursion, we defined for dB-kite, this one. Write u of omega k plus 1 with all the terms that only depend on omega k. And yeah, so the right-hand omega k plus 1 dependency. And similarly, these things that depend on omega k, can be rewritten as the ones that depend on omega k minus 1 and so on. So if we continue this until we only get the exponential around omega naught, which is the initial state that we assume we know, then we can compile any u of omega k with these elements. Okay, and we call this kind of implementation as unfolding implementation because we unfold u of omega k plus 1 in terms of u of omega k's and stuff. There's a problem though. So when you want to write u omega k plus 1 in terms of u omega k, for each u of omega k plus 1, it contains 3 calls to exponential of I t omega k. And if you want to replace this with omega k minus 1, you again need 3 calls for each of them. So at the end, exponential of I omega k requires 3 to the k calls to the initial reflection. And the circuit depth for the entire thing will grow exponentially. If you look at this form, it's kind of like you undo the previous step, you reflect around this thing, and you redo the previous step. So it's kind of redundant, and that from there emerges the exponential circuit growth. Just to make our main topic of the talk seem nicer, I was presenting it in a bit of a pessimistic way, but actually, despite this exponential growth, I want to say that our dB-kite algorithm is nice because we could actually prove that the state you have is exponentially converging to the ground state every time you do the iteration. So although it is exponentially deep to do the circuit, we get another exponential convergence. So maybe that's good enough for some purposes.
Can I answer that question? I mean, so that's two exponentials fighting against each other, right? The good one and the bad one. Hopefully the good one wins. But there's no gap in your expression, right? No spectral gap. Is that a bug or a feedback?
Spectral gap for
the Hamiltonian. That's
it's somehow embedded in alpha. So
it's embedded, so that it's implicit in alpha. So in that
yes.
It's small gap or no gap, then this will blow up, presumably, right?
Yes, no gap, then you don't get any.
Okay, so there is a gap just now.
Yes. Yep.
Yeah, but then if there is because when you develop your expression, you also need to evolve with the given Hamiltonian, that you assume that you can do this. But yeah, if there is a gap, then you can draw the rest and find the ground state also with adiabatic evolution, say, no? Or how would it compare with? Because if I have a gap Hamiltonian and it has a gap, I can do adiabatic evolution to reach the ground state, right?
Yeah, so
The whole part, but the factor, right? So it's not clear what you're moving. Sorry.
yeah, so there are other ways of preparing ground state, and I want to frame it more as an alternative way of doing it. And one nice feature of our technique is that we have a guarantee that each step improves the ground state property, and we can just replace this u of omega k by any approximate ground state preparation scheme. And by just doing this u of omega k 3 times, we can actually get an even better approximation of the ground state. That is like a factor better. Yeah.
And maybe lastly, sorry, you say that with exponential depth, you get an exponentially good approximation. Does that mean that with polynomial depth, you get a polynomially good approximation?
So yeah, but each steps are exponential, so you can just like code it in the first few steps and compare the exponentials from like this versus this. So the numerics still under development, and analytically, it wasn't like very clear if it was like really one-to-one. Yeah. Yeah. So, and we have some other guarantees and nice properties in this paper. So please check this preprint for other details. But yeah.
Do you have any guarantee or any explicit expression of lifestyle? Like
Yeah, we do have it in the paper. And it also depends on the duration. It depends on the Hamiltonian, the ground state gap and all the
And the operator norm, which sets the scale, I guess.
Yes, yes. Yep. Okay. So even classically, we can find very similar recursions. For example, this is like the most naive way of defining the Fibonacci sequence. And if you've actually tried to write this down in your like favorite programming language and run this recursion, you will notice that it takes exponential time to evaluate f of n. And that is because whenever you call f of n, you call f of n minus 1 and f of n minus 2, and n minus 2, n minus 3, n minus 3, n minus 4, and so on. So, and because you don't store your result in your memory in this naive definition, you are recalculating the same thing again and again. Like in the quantum recursion, you undo and redo the thing again and again. So in this classical example, that's the reason of the exponential time complexity. And for classical problems, people already found a very nice way to circumvent this problem, which is called memoization. Basically, you check if the result is already in the memo or not. If it is already in the memo, you just output that result. If it is not, you calculate it and you store it in the memo, in your memo pad. So in this way, you calculate each Fibonacci sequence only once. So time complexity linear to n is required. But to write down all the results, you will need a memory with space scales with the number of sequence n. Okay, so memoization converts the exponential circuit depths in some sense and constant circuit widths into linear circuit depths and linear circuit widths in my language. Okay, so our motivation was to kind of apply this technique into the quantum realm and somehow solve our exponential circuit depth problem. And we did achieve that. We reduced the exponential circuit depth into something polynomial. But in the quantum case, there's a more severe trade-off of the depths and widths. So we cannot get this linear memory size, but we need to have exponential. And I'll explain why that is the case. Okay, so this is like a general form of quantum recursion where your state is evolving by a unitary that depends on the state itself. And we assume that we know the initial state and we can do your bro node. Okay. And often this can be approximated by this product of the unitaries, where V naught, V1 to VL, we know what they are, and they are fixed for any different rule.
And that's an approximation operator norm, I suppose.
Yes. Or sometimes the algorithm is just given in this form.
Okay.
Like the dB kite. Yeah. And the state dependent parts are separated in this way. Exponential of I f of rho, where f is some function of rho that is Hermitian preserving. Just if you can approximate in this form, we call this recursion to have L memory calls, because each of this exponential of I fi of rho, we call it memory call, and we have L of them for each recursion unitary. And if the memory calls are covariant, meaning that they are in the form of exponential of IT rho, so F is just identity, then you can do the unfolding that I introduced in the dbKite for any generic covariant memory call quantum recursions, and implement the circuit for this U of rho n using exponential memory calls to the initial state exponential of the initial state that we know. And so circuit depth grows exponentially, and the factor is 2L plus 1, where L is the number of memory cores. So if we want to do the memoization for these kind of problems, we need to find how to store the previous resulting states and how to query them to use them at later steps. So two problems we have: how do we carry these memory states to implement the memory calls? And second problem is like each time we carry, because these are quantum states, we kind of spoil the memory state, and we cannot really clone the memory states to have multiple memory states. So that's another problem that we need to solve. We'll solve the first problem first. So this is what we want. We have a working register, and we input the memory register, and we do something that is fixed and that we can do without knowing this memory state and the working state, because in general, we don't know what the memory state is. And we want to achieve what we want. Okay. This was introduced in 2014, and this is called density matrix exponentiation, because at the end, it approximates the evolution by the density matrix exponentiated. And here we input the working state and the memory state, and the fixed operation that is oblivious to memory and the working state is the exponential of swap operator, where S is this swap. So you do the exponential of swap to rho times the sigma, memory times the working state, and you trace out the memory state afterwards. And then, surprisingly, this approximates this unitary evolution of sigma, the working state. And the implementation error is like proportional to the t squared. T is the duration. However, we can somehow like chop it off, like totalization, and make an evolution by swap 1 over m times shorter, and repeat this m times. So if we call this a single memory usage query, if we make m memory usage queries with shorter durations, we can reduce the error arbitrarily small. So the error will proportional to 1 over m, and by just increasing the number of queries m, we can make it precise. Okay.
And it's also non-adaptive, right? I mean, of course, the whole thing's adaptive, but once you, like in each step, it's you just repeat the same procedure.
Yes, yes. So there's no measurement, there's no anything. You just put two states, swap, measure.
He actually got into state.
Yes, yes, yes. There's also a generalization of this scheme where you can do other things, not just exponential of I rho. So you can actually do any exponential of I n of rho, where n is some Hermitian preserving map, by replacing the swap operator with this operator n, where n is the partial transpose of the Choi matrix of the intended Hermitian preserving map n. And we again have the error, and again we can reduce the error to an arbitrarily small number by just chopping this up and repeating this m times. So for each recursion, we can replace all these memory calls, exponential of I and of rho, by this memory usage queries. And if you want the error to be bounded by epsilon, we can use epsilon 1/epsilon times L copies of rho and the constant depth circuit. Well, not constant, but like L/epsilon, but not exponential to n circuit by using this memory usage query techniques. So yeah. And this is possible without actually knowing what state rho is. Yeah.
Right. The maps N1 to NL, how are you defining?
Sorry, which one?
N1 to NL.
I changed the notation a bit, but these are actually the F's here. So it is, so U of rho is determined by the algorithm. And we approximate this with this product of different unitaries. And that of decides this form of the function.
Not recursive?
No, it is recursive. This is like a single recursion step. And you repeat it with different rho, but same width and F. So if you remember this quantum imaginary time evolution thing, we note some Hamiltonian evolution, V1 some Hamiltonian evolution, and in the middle we had like exponential of I rho, right? So in that case, L is 1 and F1 is just identity. And for other algorithms, we might have some different forms of Fs. Yeah, so this function Fs are fixed for each step. And we just change this rho part for each recursion step. Yeah, so the second problem where we could not clone the memory states, we just solve this problem brute force by preparing many of them just in parallel. And this is the reason we have exponential depth circuit widths at the end. So our idea is basically replacing the last step, U of rho n minus 1, which with the unfolding requires the circuit of depths 12 plus 1 to the power of n. We replace it by this number of copies of rho of n minus 1 and some circuit whose depth is just L/epsilon. So, and because the entire circuit depth is dominated by this last recursion step, we reduce the total circuit depth by a factor of 1/12 plus 1 by just replacing the very last recursion step with this memory usage queries.
But it's still exponential, right?
Yes.
It's like in the worst moment of the exponential, you chop off the last bit.
Yes, yes. Because we only replaced the last step.
Okay.
We can try to continue this. We can replace the second last step with this number of copies of rho n minus 2 and the circuit of depths the same. And we reduce the depths by another factor of 1/12 plus 1. And there's a caveat though. So if we replace the second last step by this thing, we actually end up preparing rho of n minus 1 tilde, which is different from the exact state we want rho of n minus 1. And for the last step, then we need to use this rho of n minus 1 tilde as a memory state instead of rho of n minus 1. And this error in the memory register, rho of n minus 1 tilde, transfers to your working state every time you carry this memory state. So if you want to replace the entire n steps with this dynamic programming approach, the errors will accumulate exponentially. So that's very sad.
So could you say again, where does this error come from? Was this what you
Ah.
showed, was in what you showed with the swap thing, for instance? Where we have
So-
this expansion?
Yeah, so this thing itself has an error,
Yes, okay.
and you can reduce it arbitrarily small, but that means you need more copies and deeper circuit depths.
Thanks.
Yeah. But I want to highlight that this exponential blow-up is not just for dynamic programming, because the unfolding needs exponential number of unitaries, exponential number of unitaries that carries the initial state, which will also be erroneous. And because we are using that thing exponentially many times, that error will again blow up. So yeah, it's not just our problem. And yeah, so in my opinion, the more practical thing would be hybridize this unfolding approach with our dynamic programming approach by first execute N1 iterations with this unfolding approach and do it like in parallel this number of times. And this unfolding approach will require the total depth of exponential of O of N1. And then, because we did it in parallel, we will have access to many copies of rho of N1, and we can use them to do the dynamic programming. And we'll be able to apply N2 more iterations of this quantum recursion. So at the end, we will obtain rho N1 plus N2. And if you compare this to a no hybrid approach, when you only use the unfolding, because of the circuit depth restriction you have, you'll only be able to prepare rho N1. And if you only use QDP, because of the circuit width restriction, you will only be able to prepare rho N2. So by hybridizing these two approaches, for a fixed quantum device that has a limit on circuit depth and the circuit width, you can kind of optimize the utility of that device. And yeah, I just mentioned that the error blows up exponentially and we can not continue this forever, but sometimes we can. And that's actually our main theorem. So if the recursion is nicely converging, so if all the isospectral states converge rapidly to a fixed point, then QDP can implement n quantum recursions with any final error epsilon, and circuit depth just quadratic to the n, not exponential. And if your initial state is pure, this depth requirement becomes linear, and you need exponential number of copies where the exponential factor is like epsilon to the minus n. So this is the depth width trade-off that I advertised in the beginning. The basic idea of the proof is that because of this converging property of the quantum recursion, unitary errors get suppressed quite nicely. But the non-unitary errors kind of accumulate, and we need a separate protocol to suppress them. And when your state is pure, this separate protocol actually exists, and it's not very inefficient. Yeah, so that separate protocol is mixed-list reduction subroutines, we call. For a single qubit, it was developed in 1999 by Sirac, Eckert, and Machiavello.
So that's this old purification idea when purification was still called like that and not
Yes.
distillation, right?
Yes. And surprisingly, the higher dimensional generalization was explored quite recently by Andrew Childs and other people in 2023. So basically, if you have this mixed state rho with eigenvalues ordered, you can do the swap test and obtain this state that is proportional to rho plus rho squared. So your highest eigenvalue becomes amplified and all the other things will get suppressed. This is a circuit diagram for that and some performance from this paper by Andrew Childs and others. Yep. Oops. Yeah, so using this technique with our dynamic programming, we can suppress the non-unitary errors for the pure states, which basically make this pure state more mixed. So because of the QDP, the pure state will be mixed a bit, and we apply this mixedness reduction subroutine to make it pure again, more or less pure again. And this just, the cost of this protocol is that we need more copies of the states to make it purer, but we anyway need exponentially many copies, so it's not a very big deal to us. Okay. Yeah, so now I should argue why this trade-off is nice. First, I will analyze the volumetric measure of the quantum circuit. Volumetric, I mean circuit widths multiplied by the circuit depth. And well, arguably, this is one of the measures that people care about. And this one of our referees really like this. So for the unfolding implementation of n-step recursions, we need volume 12 plus 1 to the n because the width is constant and the depth is this thing. And for our dynamic programming approach, if we use small m memory cores for each memory core, we will use m times l plus 1 copies of the memory state for each recursion. And that means our circuit volume will scale like this, ml plus 1 to the power of n. If just using one memory core for each memory core is good enough, then our QDP circuit volume is actually exponentially better than the unfolding one. And this can be the case where your unfolding unitary is already quite erroneous, so this error from QDP is just comparable. Sadly, if m is equal to or larger than 2, there is no volumetric advantage of our technique compared to the unfolding. However,
What does volumetric mean?
just circuit width multiplied by the
this
depth.
sense.
Yes, yes. Yeah, so the
Okay, it's not like the standard quantum volume, but in this sense.
yes, in this sense, yeah. However, there are still some nice features of our QDP circuit.
We're going to comment on this, like related to a discussion yesterday. I mean, as we have also discussed many times in the group, I mean, there's many obstructions against deep circuits, but there's not so fierce obstructions against large circuits. So in a way, trading size for depth is not such a bad idea. Okay. Maybe it's weird, but I think there's an element of truth to this. No.
And I think it's particularly better for yeah, I want to convince you that it's better because especially because our QDP circuit has a very particular structure. So if you remember the scheme, you have multiple copies of rho n independently prepared, and they just interact with pairwise. So I jumped to this point, but so it has some sort of a tree-like structure where circuits that prepare different copies of row n-1 are completely decoupled before these memory states are used for the memory query. So in principle, if you imagine this distributed kind of scenario, they can be prepared in a different quantum hardware and just teleported back when they are needed. And they are needed only once for the algorithms. And at each recursion step, at each memory usage query, we put these two states, we interact them and trace out one of them. So every time we do this, we are tracing out a majority of the circuit. So the circuit width contracts exponentially after each recursion step. So it's not like exponential circuit width from the beginning to the end, but it's exponential circuit width in the beginning, but only constant width at the end. So that can be another beneficial point for distributed quantum computing scenarios. Yeah, and also unfolding kind of assumes that memory calls are in the form of covariant memory calls, so basically exponential of I row. But there might be quantum recursions whose memory calls are in a more complicated form. And in those cases, you need to approximate those complicated things with this simple one. So if you remember this dB chi thing, we started from the exponential of the commutator, which is more complicated, and we approximated it with exponential of I row and sandwiched by some other unitaries. So when we are doing this for unfolding, there are possibilities that the number of memory calls will get increased by this approximation. And in that case, we will compare not 2L plus 1, but 2L prime plus 1, where L prime is larger than L, potentially. Sorry. Yeah, so these are the I'm still getting adjusted to the climate. Yeah, these are the benefits I want to advertise for quantum dynamic programming. Now, some other examples of quantum recursions. This is actually a very cute example. So the Grover search is basically, it consists of reflections around your target state, tau, and your initial state, psi, and the iteration of it, right? So you start from psi, you reflect around tau, around psi, around tau, around psi, and at the end, you achieve some state that is closer to the target state, tau. It turns out that it can be made recursive. So rather than repeating these reflections around tau and psi for a very long L, you can kind of shorten the number of reflections, and you will achieve some state psi 1 that is closer to tau than psi naught, but not very close yet. And then you can kind of restart or reinitiate this Grover search by considering psi 1 as the initial state rather than psi naught. So now you will reflect around the same target state and the new initial state psi 1, and so on. So if you write it in this way, this precisely becomes the L memory call quantum recursion, whose memory calls are in this covariant form. And these two recursive version and non-recursive versions have more or less the same performance, in a sense that if you implement this recursive version with the unfolding with the exponential circuit depths that kind of performs the same as the non-recursive version with exponentially large L. So with the same circuit depths, they kind of prepare more or less the same state.
And that's what performance means.
Yes, yes. And because this is quantum recursion, we can try to make it dynamic without this exponential circuit depth blow up. And that means we can exponentially reduce the circuit depth for the usual global search, which is too good to be true in some sense, because there's a hard proof that this sampling-based global search has no quantum advantage. And our quantum dynamic programming is also sort of a sampling-based global search, in a sense that you start from many, many copies of psi naught, and you use them to do the global search. So we do achieve the exponential circuit depths, but the number of samples we need scale classically, not quantumly. So very cute example, very easy to understand, but sadly not useful. Another recursion is the double bracket iteration. And the quantum version of it was first proposed by Marek in this quantum paper. And the purpose of this iteration is to diagonalize your state rho into any preferred basis of yours, for example, computational basis. And the recursion is in this form, where rho is evolved by exponential of the commutator. And commutator with some diagonal matrix in diagonal in your preferred basis. And it is proven that this kind of iteration is exponentially converging, which we need for the quantum dynamic programming. So we can actually apply our quantum dynamic programming for this.
What does this mean, this diagonalization in the base that you
So
take
if
the diagonal part? What does it mean? Is to take the diagonal part and put it in the computational basis, or?
So if you have rho naught that is in some basis,
Yeah.
You unitarily transform this rho naught into rho infinity, and rho infinity will be will have the eigenvectors in the computational basis.
So to map each eigenvector to a computational basis state.
Yes, yes. And yeah, again, this can be implemented with unfolding with some approximation that we had. And this algorithm is used, for example, to again prepare the ground state. So here the idea is to diagonalize so you find a way to diagonalize the Hamiltonian by using this DBI and kind of inverse that unitary that diagonalizes the Hamiltonian to map your initial computational basis state into the Hamiltonian eigenvector.
And this paper is the Abu Dhabi numerical paper.
Yes, yes, yes. With Matteo, Eduardo, and Andrea.
So you have a Hamiltonian and you construct the K that takes the computational basis to the eigenbasis of that Hamiltonian.
Yes, yes. So you can prepare the ground state, you can prepare, I don't know, any excited state you want. I think you can choose which eigenvector you want to prepare. Although in this paper, we only focus on the ground state because that's the most important one, probably. Okay, so this is another example where we can apply the QDP. Because this is like a mixed state evolution, we probably need to take the hybrid approach. There is another cute algorithm that we propose in this QDP paper, which we call oblivious Schmidt decomposition. So if you have some entangled state, pure entangled state, this will have some Schmidt decomposition into some Schmidt basis. And basically we want to transform this Schmidt basis into the computational basis. And this is kind of the same as diagonalizing the reduced state of this pure entangled state. So we use the double bracket iteration to do that and obtain this psi infinity whose Schmidt basis is in the basis of D. And this is nice because our states are pure and we can use the more efficient version of QDP. This one is kind of speculative and I'm not mentioning in the paper. But we can imagine some like any sort of nonlinear Schrodinger.
I'm sorry, what are the performances of the previous?
Performance, you mean like required?
Yeah, resources that you consume to bring the compositions again to the computational.
So because this is we use DBI for this one. We know that this is the diagonalization is converging exponentially. So like the off diagonal elements get suppressed exponentially fast. We don't have like a very explicit performance analysis of this OSD one. I believe Marek is trying to implement it in a real like device and stuff, but yeah, we still don't have it yet.
Okay.
Yeah, so yeah, my speculation is that if you have this kind of nonlinear Schrodinger equation that nicely converges to some fixed state, then we can use the same machinery of discretizing it and making it dynamic if this F is in a nice form. And yeah, I hope this QDP can be some sort of general framework for tackling some of these problems. Yeah, so this is the last slide. Take-home messages. Quantum recursions are expensive. Either you need exponential circuit depths or exponential circuit widths. And QDP is very effective to solve the exponential circuit depth problem, especially for a few last steps when you use it in a hybrid way. And lastly, by our theorems, sometimes QDP can actually replace the entire recursion and truly making the circuit depth polynomial to the number of steps. Right, that's all for my talk. Thank you.
I've got some more questions if there are any.
Okay, I will start maybe can you say, I think it's the same as Lorenzo said, no? I mean, this algorithm that you give me Hamiltonian and I prepare the gate that takes me the computational basis to the basis of eigenstates, this seems super powerful and super cool, no? So what are the performance characteristics? So are there some properties that these objects must satisfy in order for them to be efficient or what? Because this is super cool, no? This cannot be true in all generality. I mean.
Yes. So it's kind of similar to this kite problem that we have. The exponential convergence rate depends on all these things like the gaps and the etc. And also the duration as that we need for the discretization depends on these things. So if you have a very difficult Hamiltonian to solve, this duration like needs to be kind of short, and you will need more recursion steps for fixed duration of the flow. So yeah, in a sense, it's not like perfect. And certainly the exponential circuit depth growth for the unfolding implementation is a problem. But actually in this paper with the Abu Dhabi people, we did quite a lot of numerics to actually heuristically see how good this is. And this convinced ourselves that it's kind of nice. to prepare the eigenstates of the Hamiltonian.
Just very quick, what information do you need to know? For instance, that D is the spectrum of the diagonal with the eigenvalues.
So that's a part because he presented this yesterday. Very good.
Yeah.
So sorry,
So what kind of information do you need from the Hamiltonian to actually implement these things? Or I think that D is maybe the diagonal matrix with the eigenvalues. Don't you need to know the eigenvalue?
So yeah, for this paper, we don't use rho, but we use Hamiltonian instead. D is something just we can fix. It just needs to be diagonal in the computational basis, and so we need like the evolution by the Hamiltonian. So that is one thing we need, and to determine the duration S, we need some information about the Hamiltonian, especially the operator norm and the gap. I believe I forgot the exact form, but yeah, it's either the operator norm or the gap or both. Yeah.
Thank you.
I mean, super nice. Very impressive. And on the generalizations you mentioned, there's kind of two ways to tackle that, right? And one thing is like to look at other nonlinear Schrödinger equations to be tackled, right? Like, I don't know, differential equation type. And the other one would be to fix the takeoff merit in the flow and then see what other flows come out when you change the takeoff merit in the flow, right? That's a different way of generalizing.
Yes. So the double bracket flow, where F is just a commutator,
Yes,
that's like the gradient flow for this particular Riemannian metric, right?
exactly.
And if you
Then,
change the metric,
in
then
principle, you can just fix the pair of the metric in the generator, and then you get a new package of that type.
yes.
Then I guess the other one, thank you, speaker again.